The idea of loco and absolute mins and maxes from Calc 1 apply here to surfaces in 3 space that we're working with now. It's really the exact same idea with a logical extension to 3 space. So, like, take a look at this function. Clearly, I have this mound. No matter how I spin it, this is the highest point in some region, some disk around AB. We think of where this is f of AB, so AB is the x and y coordinates. Likewise, down here, this is a local minimum, because no matter how I spin it, this point down here will be the lowest point for some disk around it. Likewise, if I consider something that looks like this, I have a local maximum that appears up here, and another one that appears, at least that appears to be humped up right there. And no matter how I spin it, it does appear to be a mound. So there's a point up here, f of AB, so that some disk about it, that this point will be the highest point in that region. On the other hand, something like this does not have a local min or max. If I look in the x direction, it appears to be parabolic. So it would have a minimum in terms of x, but in the y direction, you can see it's also parabolic, but it's in the opposite direction. So if I pick a point here that appears to be my minimum in the x direction, that also appears to be my maximum in the y direction, this is not a local min or a local max. That's actually referred to as a saddle point, possibly for obvious reasons, because it looks like a saddle. Now, the definition for mins and maxes in 3 space is very similar to what we're used to using in terms of working in 2 space. Now, a function of 2 variables has, sorry, I can see a couple typos here already, has a local maximum at AB if f of xy is less than or equal to f of AB when xy is near AB. That's the idea of if I have some point of coordinates AB on the xy plane, then f of AB up here somewhere, this curve goes like this, and no matter what direction you go, this is the maximum. So AB is on the xy plane, and z is f of AB. So the number f of AB is actually referred to as a local maximum value. Now, if f of xy is greater than f of AB, that's a situation, let me erase some of that, where here I still have AB on the x-axis, but everywhere I look, f of AB is like the small point. I think you get the idea there. So f of x, no matter where you are in this some region about it, some region about AB on the xy axis, when I translate these points up to the function, no matter where I am, f of xy is bigger than f of AB, then that is what we refer to as a local minimum value. Now, Fermat's theorem for function of 2 variables actually tells us, in a sense, how to find these local mins and maxes. Now, if the theorem says if f has a local min or max at AB, and the first order partial derivatives of f exist, then those partial derivatives will in fact be 0. Which kind of makes sense intuitively, because how do we find candidates in 2 space for local mins and maxes? We took the derivative and we set the derivative to 0, or when the derivative was undefined. So those were our candidates. Well, now we're in 3 space, we need to take a look at the derivatives essentially from both directions. So the concept here really should not be anything new.